Hello everyone, this is Jing Gu. Today I'm going to present our paper Vision and Language Navigation, a survey of tasks, methods, and feature directions. First, let's look at this example. A human asks a robot to get an apple, so then the robot understands that instruction and answer, sure, I will get the apple for you. We can understand such a robot would be very useful in reality. So first, it could release humans from repetitive tasks and dangerous tasks. Secondly, it also explores the path to real artificial intelligence from the perspective of robotics. So what is vision and language navigation? Vision and language navigation, or VLN, means building an agent with language ability to navigate in environment to execute tasks. It usually contains two inputs. First, current visual observation. Secondly, natural language instruction from the human, what the agent needs to do. Then the output would be what action to take at the current step. And there are three elements: environment, agent, and oracle. First, in VLN, there would be interaction between the agent and the environment. In other words, each time the agent makes a step or makes an action, the environment will render new observations. Secondly, there would be communication between the oracle and the agent, and the communication would be in natural language. Third, there would be interaction between the oracle and the agent. Sometimes the oracle needs to watch what happened in the environment to provide the guidance. Sometimes the oracle and the agent, they could even collaborate with each other in the environment. Now let's talk about the datasets. Here we can see, since the first VLN dataset, room to room R2R, is proposed at 2017, there has been many datasets proposed in this domain. And here we are basically using two dimensions to categorize those datasets. The first is communication complexity. It means the level at which the agent may converse with the oracle. The second is task objective. It means how it describes how the agent attains its goal based on the initial instruction. Here we give some detailed explanation and some examples. For the communication complexity, we have three levels. First, the initial instruction. It means the oracle will only give an initial instruction to the agent without further guidance during the navigation process. The second is the oracle guidance, which means the oracle will provide further instruction during the navigation process. The third is dialogue, which means the oracle and the agent, they communicate freely during the navigation process. They collaborate with the language to achieve the tasks. And that is more like what two humans will do in reality. Here we also have three types for task objectives. First, fine-grained. It means that at the beginning, the oracle will give a very detailed instruction for the agent about what to do step by step. It could also be coarse-grained. In that case, the oracle will only give a high-level instruction, and then the agent will need to figure out how to achieve the goal by itself. Sometimes, if the task is too complex, then the agent needs to do both navigation and interaction to achieve the task. As you can see, with these two dimensions, we can categorize them into this table, and yeah. Here we describe how to actually build an agent. Before we introduce the methods, we need first to identify what are the key challenges in VLN. First, there there is too much information to process in VLN. The navigation history could be very long. And the second, here, the solution is we need to build a better modality understanding module to understand the visual information, text information, and the action information. Also, it is hard to make a correct decision after we, as an agent, understand the modalities, because sometimes the environment could be really complex. So in that case, we need a better action strategy. Third, how to do the data scarcity. Compared with other methods, the training data in VLN is quite limited. So in that case, some data-centric learning methods, for example, data augmentation, could be useful. Finally, we usually want the agent to be tested on a new environment. So failure to adapt to the new environment would also be an issue. Here, if the agent could explore the test environment and keep updating itself, then it will be more familiar with the test environment. Here, we, according to the challenge we just described, we categorize the methods into 4 categories: representation learning, strategy learning, data-centric learning, and prior exploration. First, for representation learning, it is aiming to get a better understanding for the input modalities. Pre-training, of course, it is a commonly used methods. Semantic understanding, it means we find out what are the key information in the instruction and the observation, and we extract that information first. Graph representation is also useful because there could be a complex relation between the token mentions and the visual objects. We could use a graph to represent that complex relation. Memory structure could be used to extract useful information from a long navigation history. Auxiliary tasks use extra laws to make the agent to be familiar with the environment or to be familiar with the task itself. It could be predicting the current progress or about predicting the status, like what is the difference between the current posing and the previous posing. A better action strategy will also be helpful. First, reinforcement learning, of course, it has been proven useful after the agent is trained on supervised learning. If the agent could explore several directions and choose the best one, it will also improve the performance. Then have a better planning about what to do for next, next 10 steps. That would also be helpful. If the agent is able to ask him for help actively, then it could gather more information from human. Data-centric learning also contains many important methods. First, of course, data augmentation. It provides more training samples. Curriculum learning try to train the agent from easier tasks to harder tasks. And multitask learning, different VLN agents, different VLN tasks benefit each other. And sometimes we could even interpret the instruction from a different perspective. Because sometimes the instruction could be too long or too short, so it would not be easily understandable to robot. In that case, we could interpret that first. Prior exploration is also important because it helps the agent to get familiar with the test environment before the official task execution. But however, since it has extra access to the test environment, and usually the agent is still updating itself during the test time, it is not comparable with other models without prior exploration. Here we introduce some metrics. First, of course, more intuitive. Success rate, goal progress, path length, something like that. Those metrics describe whether the agent achieves the goal or not. There is another kind of matrix, path fidelity matrix. It describes whether how much the navigation path matches the ground truth path. Here we introduce some future directions for the VLN domain. First, we could do some improvement on the current tasks. For example, usually current methods do not use external knowledge, but how to explicitly use Wikipedia knowledge, that would be very helpful. And also, current datasets or benchmarks, they usually lack diversity. How can we solve that problem and even make it more generalizable to unseen new environment? We could also do some new topics in VLN. For example, first, collaborative VLN. How can we build several agents at the same time and they could collaborate with each other and even with human? Also, how to transfer things from simulation to reality. Lastly, how can we handle the ethics issue and some privacy issue? How can we analyze the cultural difference in the navigation process? All these are important topics. I think that's it for today's presentation. Thanks so much. Please feel free to reach us if you have any questions. Thank you.